Since alpha of L is L prime by definition, P prime Q prime is an element of L prime because we have taken P and Q. Oh, no. Assume alpha L is equal to L prime. Let alpha of P be P prime and alpha of Q be Q prime. Since P and Q, they do not belong to L, by definition of alpha of L, their image P and Q prime, they do not belong to L prime. Suppose that P and Q are in the opposite sides of L. Then P and Q do not lie on L. Since P and Q are in the opposite sides of L, PQ intersection L is different from empty. Let PQ intersection L be R. Then R is an element of L. Let alpha of R be R prime. By definition of L prime, which is alpha of L, then R prime is an element of L prime. Since again P R Q and alpha is an isometry, alpha preserves betweenness. Hence we have alpha of P, which is P prime, R prime, Q prime, where R prime is an element of L prime. That is, the line segment P prime, Q prime, intersection L prime is R prime, which shows that P prime and Q prime are in opposite sides of L prime. Hence, A follows. B, suppose P and Q are on the same side of L. We want to show that their images are on the same side of L prime. We show that their images, which are P prime and Q prime, are on the same side of the prime. Suppose not. That is, P prime and Q prime are in the opposite side of L prime. Consider alpha inverse, which is also an isometry. Then alpha inverse is an isometry. Since alpha of P is P prime and alpha of Q is Q prime, we have alpha inverse of P prime is P and alpha inverse of Q prime, which is Q. Since P prime and Q prime are in the opposite side, so in the opposite sides of L prime, and alpha inverse is an isometry, their image, that is P and Q, are in the opposite sides of L by 1. Opposite sides of L by the above A, which is a contradiction, which is contradiction. Hence, P prime and Q prime are on the same side of. Hence, the theorem follows.